Hi there. Well, settle in. We're going to take a look here at 8.5 systems of linear equations in more than two variables. And we've got a lot to talk about in this section. Not that we always don't have a lot to talk about, but there's quite a bit here. And so let's just kind of go through a few things. I've laid this out a little bit differently because, well, we've got some different stuff to consider here. So without further ado, here we go. For systems of linear equations containing more than two variables, we can use either the method of substitution, like we talked about in 8.1, or the method of elimination that we talked about in 8.2. The method of elimination is the shorter and more straightforward in finding solutions, and it leads to the matrix technique that we're going to talk about here. You'll notice that we've got three equations and three unknowns here. Alright, and you'll notice that we're using the elimination method. We are multiplying the top equation here by -2 all the way through, and what that does when we add down -2 plus 2, 0x. -2 times -2 is +4 plus 1 is 5y. -2 times 3z is -6z minus 4z gives me -10z, and then -2 times 4 is -8 plus 3 is -5. Alright, and so we added -2 times the first equation to the second equation. That's how we got this. And then working from this set of equations, we added 3 times the first equation to the third, and so forth and so on. So let me pause the recording, or you guys now pause the recording for just a second and study what has been done there, and see then when they talk about the back substitution how they've went and plugged the z equal 2 in. Then you get y equal 3, so you plug in 2 for z, 3 for y, and then you get x equal 4. Take a moment and study that. And you probably noticed that the process we just used is a little messy. It's a little cumbersome with writing all the variables down with the coefficients. And so we're going to take the process we walked through above and apply it to a concept called the matrix. We're not talking about the movie, we're talking about the mathematical idea. And as we go through the next few examples, pay attention to the idea of the coefficient matrix and the augmented matrix. What is this matrix, and what is some notation associated with matrices? And you know what? While we're at it, let's just take a moment here. Alright, and I'm going to take that original system that we just had, and I'm going to write what is called the coefficient matrix. Now the coefficient matrix, we're just going to take all of the coefficients. So from the top equation, 1, -2, 3, 2, 1, -4, and then -3, 4, and -1. There's the coefficient matrix. Now, let's talk about the augmented matrix. There's one difference between the coefficient matrix and the augmented matrix. And that is that along with the coefficients, we are going to draw a vertical line where the equal sign would appear, and we're going to put the value after the equal sign. And so filling in all my coefficients, there's the augmented matrix, and so there's our difference between our coefficient matrix and our augmented matrix. Now, it's the augmented matrix that we're going to be working with next here to try to solve the equation. So let's move ahead here, and as our notes say, we're going to talk about some terminology. Before discussing a matrix method of solving a system of linear equations, we need to state a general definition of a matrix. We shall use double subscript notation. That means there's going to be two subscripts denoting the number of rows in denoting the number that appears in row I, column J, by A sub ij. The row subscript A sub ij is I, so row I, and column J. You'll notice here that our rows go across, our columns go up and down. You'll notice here that A sub 1, 2 is row 1, column 2. Alright. And the notation M cross N is the definition, by definition, is read M by N. We say that the matrix is M by N and call M by N the size of the matrix. It is possible to consider matrices in which the symbols A sub ij represent complex numbers, polynomials, or other mathematical objects. The rows and columns of the matrix are defined as before. The matrix in the definition has M rows and N columns. Note that A sub 2, 3 is row 2, column 3, and A sub 3, 2 is row 3, column 2. Each A sub ij is an element of the matrix. If you have the same number of rows as you do columns, we call it a square matrix of order n. And they talk about the main diagonal here, guys. This starts in the upper left-hand element and runs down here. We call that the main diagonal. Of course, you've got two diagonals here, one going from upper left to lower right, the other going from lower left to upper right. The one that those that deal with matrices are most interested in is the main diagonal going from upper left to lower right. So if you have questions there, certainly make note of those. Now, I think I mentioned this back a couple lessons ago. Theorem on matrix row transformations. I just want you to think that before, when we've been working with a system, we can change the order in which we list the two rows. Alright, we can do that. We can multiply a row or divide a row by a non-zero constant and then take that and add a constant multiple of one row and add it to another. Row transformations there. And we refer to ideas 1 through 3 here as elementary row transformations or operations of a matrix. If a matrix is obtained from another matrix by one or more elementary row transformations, the two matrices are said to be equivalent, or more precisely, row equivalent. We shall use the symbols in the following chart to denote elementary row transformations of a matrix, where the arrow may be read as replaces. Thus, for the transformation kr sub I replaces r sub I, the constant multiple kr sub I replaces r sub I. In other words, guys, what we're saying, we're going to use this notation right here. We're going to use this notation to help us keep track of what we're doing as we transform a matrix from one look to the next. We're going to talk about how to write a system using the row echelon form of a matrix. The row echelon form of a matrix. What this means is the first non-zero number in each row, reading from left to right, needs to be a 1. The column containing the first non-zero number in any row is to the left of the column containing the first non-zero number in the row below. In other words, what you notice here, we've got a 1, everything below it are zeros. Then we move over, we've got a 1, everything below it are zeros. We don't have to have a 1. We don't have to have a 1, but we do, once this 1 has been put here, everything here needs to be a 0, etc. Rows consisting entirely of zeros may appear at the bottom of the matrix if you so desire. They do not have to appear at all. And so we've got some guidelines here. It says locate the first column that contains non-zero elements and apply elementary row operations to get the number 1 into the first row of that column. And then we're going to work to get zeros underneath it. So in other words, we're going to make a 1 here and we're going to get zeros below it. And then we're going to locate the next column that contains non-zero elements and apply row transformations to get the number 1 in the second row of that column. Notice how we got a 1 here, and that's the first thing that we've got. Alright, and we know we're going to be in row echelon form when we get 1s down as far as we can get them. I think, guys, that the easiest thing to do here is to just jump in and do an example. You're going to see that this is incredibly tedious work, and so what I'm going to do is show you how to do this by hand, and then I'm going to show you how to use a calculator command to check your work. What we're going to do here is we look at example 1. It says by hand reduce the matrix to row echelon form, and then use your calculator to verify your answer using this RREF command that I will show you in a minute. What we need to do, guys, is write the augmented matrix, pulling the coefficients here: 1, 3, -1, bar, -3. Row 2, our coefficients are 3, -1, 2, 1, and then row 3 we have 2, -1, 1, and -1. Now what we need to do here, we've already got a 1 in this position. This is good news. Now we need to make zeros in these two spots. To do that, what I'm going to do is I'm going to take row 2 and I'm going to subtract 3 times row 1, and this will be what replaces row 1. I'm sorry, this is going to be what replaces row 2. Now let's go through this. Okay, row 1, folks, is staying the same. 1, 3, -1, bar, -3. Now here we go. Row 2. 3 minus 3 times row 1. So 3 minus 3 times 1 is 0. -1 minus 3 times 3 is -10. 2 minus 3 times -1 is going to give me 5. And 1 minus 3 times -3 is going to give me 10. And then for our third row, I'm going to take our third row and I'm going to subtract 2 times row 1, and this is going to give me my new row 3. So 2 minus 2 times 1 is 0. -1 minus 2 times 3 is -7. And then 1 minus 2 times -1 is going to be, let's see here, 1 plus 2 is going to be 3. And then -1 minus 2 times -3 is going to give me 5. Okay, so good news. We have gotten a 1, upper left, zeros below it. Our next task, guys, is to work right here. We want to turn that into a 1. And so what I'm going to do is take -1/10 of the current row 2 and use that to replace row 2. Now my top equation, my top row stays the same. 1, 3, -1, -3. Now here comes the change. 0 times -1/10 is 0. -10 times -1/10 is 1. -10 times 5, -1/2. -1/10 times 10, -1. And we are leaving the bottom row the same at this time. We'll worry about making the needed changes in our next step. And you say, well, what change is needed? Well, the thing that I need zeros below the ones in my main diagonal. And so I'm going to somehow have to turn that -7 into a 0. Notice what I'm doing. I'm circling the elements in the matrix that I'm looking to change so that I can kind of keep track of what I'm doing. And so what I'm going to do here is I'm going to take 7 times row 2, and I'm going to add that to row 3, and that'll replace row 3. So here's what's going on. Row 1 stays the same. 1, 3, negative 1, negative 3. 0, 1, negative 1 half, negative 1. And then, now here comes our change. 7 times 0 is 0, plus 0, still 0. 7 times 1 is 7, minus 7, 0. 7 times negative 1 half is negative 7 halves, plus 6 halves is negative 1 half. And 7 times negative 1 is negative 7, plus 5. This gives me negative 2. Alright, so I have got this guy to be a 0. And now what I need to do is I need to make this element into a 1. I need to make this into a 1. I'm going to take the row 3 that I have now. I'm going to multiply it by negative 2, and that will become my new row 3. So the top row stays the same. 1, 3, negative 1, negative 3. 0, 1, negative 1 half, negative 1. And then now we're going to multiply by negative 2 times 0 is 0. Negative 2 times 0 is 0. Negative 2 times negative 1 half is 1. And negative 2 times negative 2 is 4. So notice we've gotten what we want. We want 1s down the main diagonal, and we have 0s below all of those 1s, and that's our goal. Now, you say, okay, well, what's this do for us? Well, here we go. This gives me 3 equations. 1x plus 3y minus z equal negative 3. 0x plus y minus 1 half z equals negative 1. And z equal 4. Well, this is good news. We found z. Notice if we know z, and we do, we can plug it in right here. Y minus 1 half times 4 equals negative 1. Y minus 2 equals negative 1, so y equals 1. Now we found z, and we found y. I can plug that in here. X plus 3 times 1 minus 4. This equals negative 3. X plus 3 minus 4 equal negative 3. X minus 1 equals negative 3. X equals negative 2. And so we've got our solution. And instead of writing an ordered pair, you remember an ordered pair is x, y. Well, we're going to use what we call an ordered triple. And an ordered triple writes the coordinates x, y, z. Still in alphabetical order. X is negative 2, y is 1, z is 4. Okay, so while we have here a fairly lengthy process, it's not nearly as lengthy or as messy as it would be if we were carrying all of those variables around with us. So pause the recording if you need to study what we've done, and when you are somewhat comfortable with what we've done, let's jump in and take a look at another example. Oh, I almost forgot. Before we do that, let's take a minute and check this out by hand, or by using the calculator. Alright, I've gotten my calculator out. Hopefully you have as well. And so what I'm going to do is show you how to enter a matrix onto the calculator. Now you'll notice over here on the left right here above the X inverse key is we have the matrix button. So we're going to hit second and then that key, and that's going to bring up for us different matrices that we can go into. Now what we're going to do here, folks, is we're going to enter a matrix that has 1, 2, 3 rows and 1, 2, 3, 4 columns. So we need to edit. We'll use the right arrow key to go over to edit. We're going to edit matrix A, so I'm going to hit enter. We're going to tell the calculator that matrix A is a 3 by 4 matrix. And we're going to look at the numbers that we have here. We have a 1, a 3, and we just hit enter to move over to the next element, a -1, a -3, a 3, a -1, a 2, a 1, a 2 on the third row, a -1, a 1, and a -1, and we hit enter. And now once we've got our elements entered, we can quit out of this second mode. If we go back to our matrix menu, second inverse, this brings up my options. If I hit enter on matrix A and then hit enter again, you can see the matrix that we've just entered. 1, 3, -1, -3 across row 1, 3, -1, 2, 1 across row 2, 2, -1, 1, -1 across row 3. And now what I'm going to do, I can do two things here. I can do two things. I can go to the matrix menu once again. This time I'm going to go to the math option because we're going to do some math. And let's hit the up arrow key. And you'll notice that option A is REF, row echelon form. And so we are going to hit enter there and ask the calculator to do a row echelon form on, and I've got to go back to my matrix menu and tell it that we want to work with matrix A. Row echelon form on matrix A, and I hit enter. And the other cool thing I can do here, folks, if I hit math and then option number 1, it's going to change any decimals I have into a fraction. And you'll notice that as we use the right arrow key here, you'll see the fraction showing up. You'll see a version of a reduced echelon form. Now you say, hey Kev, this does not exactly match what I did or what we did. That's true, it doesn't. You're going to have that based on the way your matrices can be manipulated. Alright, so we can check here, but this doesn't instantly tell us what our answer is. So what we're going to do instead, we're going to pull our matrix menu back up. We're going to do the math option. Once again, we're going to hit the up arrow, but this time we're going for option B, as in boy, RREF. You'll learn if you take a linear class or a finite class that this stands for reduced row echelon form. This requires a little more work. On the other hand, it produces a little cleaner result. We bring about our matrix, we're going to perform the operation on A, and we hit enter. Now check this out, folks. This is pretty cool, huh? Look at this. 1x equals -2, 1y equals 1, and 1z equals 4. Please notice how the elements in the right-hand column are representing the solution that we just found using row echelon form. Question comes up, why would we need to go to all the trouble to show the work of row echelon form? Why can't we just punch this in the calculator and check our work? The department at this point in time feels it is important at this level of the game to be able to perform the hand manipulations. Certainly we respect the wishes of the department there. However, I am showing you how you can check your work on the calculator. I would encourage you to do that. I will mention that the calculator, if you look at the matrix operations, it is capable, if you look at math, it is capable of doing some of the other things that's going on here. We can add a constant times a row and then add that to something else, or we can swap rows. Guys, in my opinion, life is much easier just to do that by hand. By the time you fool around telling the calculator what you need to do, you could have the work done by hand. Now, that's my opinion. Others teaching the class may feel differently, but that's my opinion. Alright, so make note of any questions there. This is a little different process, I understand that. Let's jump in here and take a look at example 2. 2, negative 1, 1, 0. 1, negative 1, negative 2 and 0. And 2, negative 3, negative 1, and 0. Alright, so we've created our augmented matrix. The elements to the right-hand side of the equal sign are zeros, and we have those in place. Now, remember what we want. We want a 1 in this upper left-hand column and zeros below it. And then we want a 1 here and a 0 below. And then we want a 1 here. And we don't really care so much what's up here in the upper right-hand corner of the matrix. Alright, so what I'm going to do, folks, is I'm going to take row 1 and interchange it with row 2. There's no need to do any more work than we just have to do. Row 1 now becomes 1, negative 1, negative 2, and 0. Row 2 becomes 2, negative 1, 1, and 0. And row 3 stays 2, negative 3, negative 1, and 0. Okay. Now, we've got the 1 in the upper left-hand corner. I'm going to work on making this a negative, making that a 0, and I'm going to work on making that a 0. So my top row stays the same. 1, negative 1, negative 2, 0. Now my middle row, guys, I'm going to take negative 2, add it to row 1, and that's going to give me my new row 2. So negative 2 plus 1 is negative 2, plus 2 is 0. Negative 2 times negative 1 is 2, minus 1, which is 1. Negative 2 times negative 2 is 4, plus 1 is 5. Negative 2 times 0 is 0, plus 0 is 0. And then I'm going to take negative 2, multiply by row 1, add to row 3, and this will give me my new row 3. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times negative 1 is positive 2, minus 3 is negative 1. Negative 2 times negative 2 is 4, minus 1 is 3. And then negative 2 times 0 is 0, plus 0 gives me 0. Okay. Hey, and this is pretty sweet because I've now got the 1 here in row 2, column 2 that I need. So the next thing I'm going to do, I'm going to try to turn this negative 1 into a 0. You notice how this is a very systematic process. If you don't take things in this order, things get very sloppy, very crazy, very quickly. So what I'm going to do here is I'm going to take row 2, add it to row 3. That will give me my new row 3. So row 1 is going to stay the same, 1, negative 2, 0. Row 2 is going to stay the same, 0, 1, 5, 0. And then row 3, we're just going to add row 2 and row 3. This gives me a 0. 1 minus 1 gives me a 0. 5 plus 3 gives me an 8. And 0 plus 0 gives me a 0. So there we go. Alright, we're getting real close, guys. All I need is to turn this 8 into a 1. And if we take 1/8 and multiply row 3, we can get our new row 3. Remember, please, that the top two equations here will stay the same. 1, negative 2, 0, 0, 1, 5, 0, and then we're multiplying 0 by an eighth and getting 0, 0 by an eighth and getting 0, 8 by an eighth and getting 1, and 0 by an eighth and getting 0. So now, notice please the equations that come from this. If I take the first row, I've got 1x minus 1y minus 2z, this equals 0. The middle row, y plus 5z equals 0. And the bottom row, z equals 0. Well, if z equals 0, we're going to plug that in right there. So y plus 5 times 0. This gives me 0, and so, well, y plus 0 equals 0. Y must be 0. And then I can take the value for y that I have, in addition to the value for z that I have, x minus 0 minus 2 times 0, this equals 0. And we see that x equals 0. So we write our ordered triple 0, 0, 0. As I've mentioned, it's very handy to take our calculator and check our work. So we'll call upon our calculator here. We are going to edit this particular matrix. You'll notice once again we've got a 3x4 matrix. So I'm going to edit matrix A. I'm just going to recycle. Use matrix A, still 3x4, no need to bring in anything new. And so let's list our elements here. We've got 2, negative 1, 1, 0, and then we've got 1, negative 1, negative 2, 0, and we've got 2, negative 3, negative 1, and 0. Alright, so we've entered our elements into matrix A. Let's quit out of this, pull back our matrix menu, go over to math, and we are going to use the RREF option. We're just going to go straight to that and see if the calculator gets the same solution that we do. Again on matrix A, so option 1. By the way, I should mention, for those of you that are familiar with the second enter command, you could have done that here. This would have brought up the RREF of A, hit enter, and you would have seen that 1x equals 0, 1y equals 0, and 1z equals 0. And so there's our solution there. The calculator verifies it. Alright, so notice in these last couple examples that we've had a unique solution. The first example that we worked, our solution was negative 2, 1, 4 for the x, y, z. In the example we just worked, our solution was 0, 0, 0. And now we're going to look at a system that has an infinite number of solutions. I think we've all remember working these systems of equations where sometimes we say we have a consistent system of consistent equations, and we want to see, and we come up with an infinite number of solutions. Not only are we going to see how that works, we are going to see how we can go about representing some of those solutions. Alright, an exciting time. Let's jump in. Let's write, and I need to get my pen going again here. Let's write our augmented matrix. The coefficients here are 1, 2, negative 2, here's my bar, 4, negative 1, negative 3, 2, negative 6, and then 2, 1, negative 4, and 2. Now the good news again, if you'll notice, is that we've got a 1 in that upper left hand corner. That's pretty cool. So I'm just going to rewrite that top row. 1, 2, negative 2, 4. And if I add rows 2 and 3, I can get the new row 3. So 1 minus 1 is 0. 2 minus 3 is negative 1. Negative 2 plus 2 is 0. 4 minus 6 is negative 2. And then for the third row, I'm going to take negative 2 times row 1 plus row 3, and that's going to give me my new row 3. I said something wrong a second ago, and I realize that now. To get this second row, folks, we took row 1 and added row 2. So row 2 plus row 1 gives me my new row 2. My apologies for that. Here we come, row 3. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 plus 1 is negative 3. Negative 2 times negative 2 is 4. Minus 4 is 0. And then negative 2 times 4 is negative 8 plus 2 is negative 6. So we worked on two elements there. We worked on making that number and that number both 0. The next thing I need to do is turn this into a positive 1. Well, if we take negative R2 and replace row 2 with that guy, we'll have what we need. So we've got 1, 2, negative 2, and 4. The opposite of 0 is 0. The opposite of negative 1 is 1. The opposite of 0 is 0, and the opposite of negative 2 is 2. There we go. And bottom row, we're going to leave it alone for now. 0, negative 3, 0, negative 6. So the next thing we need to do, we need to work on this element here. I circle it so I can keep track of it. And I need it to be a 0. So what I'm going to do, I'm going to recopy my top row, 1, 2, negative 2, 4. Recopy the middle row, 0, 1, 0, 2. And I'm going to now take and multiply row 2 by 3 and add row 3, and that will be my new row 3. So here we go. 3 times 0 is 0 plus 0 is 0. 3 times 1 is 3 minus 3 is 0. 3 times 0 is 0 plus 0 is 0, and 3 times 2 is 6 minus 6 is 0. Now, we talked a little bit ago about rows of all zeros appearing on the bottom. Okay? And that doesn't tell me a whole lot. So the first equation here tells me that 1x plus 2y minus 2z equals 4. The second equation tells me that 0x plus 1y plus 0z equals 2, and the bottom equation, real exciting, tells me 0 equals 0. Well, what do we know? Well, we know that y equals 2. And so we can plug that in over here. And so we get x plus 2 times 2 minus 2z, this equals 4. So x plus 4 minus 2z equals 4. If we subtract 4 from both sides, guys, we see that x minus 2z equals 0, and x equals 2z. Now let's think about this for just a minute, okay? I'm going to write an ordered triple. X, Y, Z. Now I know what y is. Y is 2, no matter what. And x, it tells me, is 2z. Well, if x is 2z, then z is just z. And this is what we call a general solution. Now, a lot of books, a lot of teachers will say, okay, instead of z here, x, y, z equals a, b, C, and so a lot of teachers might have us write 2C, comma 2, comma C. I'm going to accept either one of those at this point. When you get into linear or finite, those of you that are heading that direction, you'll talk more about it later, but for now I just want to give you a little taste of how this works. Alright? And you say, well, a general solution, what do you mean by this, Kevin? Well, a general solution as opposed to a particular solution. So if I have a particular solution, alright, C equals Z equal, let's say, 1. Well, if this is the case, then the particular solution is 2 times 1, comma 2, comma 1, which is 2, 2, 1. Let's say that C equals Z equal 5. So we get 2 times 5, comma 2, comma 5, or we get 10, comma 2, whoops, didn't mean to put that parenthesis in there, sorry about that, comma 5. So these are both particular solutions. And I'm sure some of you are sitting there saying, whoa, whoa, whoa. Where did he get C equals Z equal 1? Where did he get C equals Z equal 5? I just pulled those out of the air. You see, this system has an infinite number of solutions, but they're all of the form where y is going to be 2 and the x-coordinate is going to be double the z-coordinate. Or another way to say that, the z-coordinate is going to be half of the x-coordinate, whichever way we choose to think about it. So here's an example of that consistent system of dependent equations that you've talked about, hopefully, in one of your prior algebra classes. Well, you can probably guess what's got to be coming next. We've had a couple matrices that had a single solution. We had a matrix that had infinitely many. And so what's left? Yep, you're right, a matrix with no solutions. Now, before we go on though, some of you are probably wondering, and I'm glad you are, hey, what's the calculator do in a situation like this? Well, let's check it out here. We'll go to our matrix. Once more, we will edit matrix A, put in my elements, still a 3-row, 4-column matrix. 1, 2, -2, 4, and then -1, -3, 2, 6, 2, 1, -4, 2. Okay, so we've entered the elements to our matrix here, and so I'm going to quit out of this. And now, for those of you that aren't familiar with this, there's a little, I don't know, trick, I guess, a little command on the calculator. See, what we want to do again is we want to row reduce this, we want to put matrix A in row reduced echelon form. If I just hit second and then the enter button, that brings up the last entry, and if I hit enter, this gives me whoa, I must have typed in something incorrectly. Let's check this out here. Matrix, edit. Let's check out here 1, 2, -2, -1, -3, 2, 2, 1, -4. We must be in the right hand column here, that we have a problem. Oh yes, there it is, 4. This needs to be a -6, so we'll type that in, -6, enter, and then the 2, we're good. So let's go back to our home screen. And let's do RREF. And now check out, we have zeros across the bottom, 1y equal 2, and 1y equal 2, and x minus 2z equals 0, and so X is twice whatever Z is, and we see that in our particular solutions here that we've written, and in our general one for that matter. X is twice whatever Z is, and that gets us to where we were by hand a little bit ago. So now, we're getting excited here now. Let's take a look at a system with no solutions. Alright, and so once again we'll start this problem just like we started the past couple. We're going to write our augmented matrix. 1, 3, -3, -5, 2, -1, 1, -3, -6, 3, -3, and 4. Now, good news is we've got a 1 already up here. So what I'm going to do is I'm going to try to make this a 0. I'm going to do that by leaving the first row the same. 1, 3, -3, -5. 2 times row 1, and actually let's make this -2 times row 1, plus row 2. This is going to give me my new row 2. -2 times 1 is -2, plus 2 is 0. -2 times 3 is -6, minus 1 is -7. -2 times -3 is 6, plus 1 is 7. -2 times -5 is 10, minus 3 is 7. And then let's also try to turn this into a 0 while we're at it. So let's take 6 times row 1, add it to row 3, and we'll get our new row 3. 6 times 1 is 6, minus 6 is 0. 6 times 3 is 18, plus 3 is 21. 6 times -3 is -18, minus 3 is -21. And 6 times -5 is -30, plus 4 is -26. Okay, and so what we have here, we've succeeded in getting our zeros right here. Now let's take a look at making this a positive 1. If I take -1/7, multiply that by row 2, I will get my new row 2. Row 1 stays the same. 1, 3, -3, -5. 0 times -1/7 is 0. -1/7 times -7 is 1. -1/7 times 7 is -1. -1/7 times 7 is -1. And then we'll recopy the bottom. 0, 21, -21, and -26. Alright, now remember we're working to get 1s down the main diagonal and 0s below them. That means the next element we need to work on is that 21 right there. Alright, and so what I'm going to do here is I'm going to take 21. Well, first of all, let me leave the top row alone. 1, 3, -3, -5. And then middle row is going to stay the same. 0, 1, -1, -1. And then what I'm going to do is I'm going to take -21 plus -21 times row 2 plus row 3, and this gives me row 3. So -21 times 0 is 0 plus 0. -21 times 1 is -21 plus 21 is 0. -21 times -1 is 21 minus 21 is 0. And -21 times -1 is positive 21 minus 26 is -5. And folks, when you see zeros all the way across the bottom row, except for the last right-hand element, you know you're done, and you know your system has no solution. check out what our equations are. The top equation tells me 1x plus 3y minus 3z equals -5. The middle equation, 0x plus y minus z, excuse me, supposed to be a z there, my apologies, minus z equal -1, and the bottom equation, 0 equal -5. Well, right there, that instantly tells me there is no solution. You might remember from your beginning algebra days that we have an inconsistent system. And you say, well, how does the calculator react when it's given an inconsistent system? Here we go, matrix. Once again, I'm going to edit matrix A. Still a 3 by 4. 1, 3, -3, -5, 2, -1, 1, -3, and then -6, 3, -3, and 4. So there we go. We've got our elements in our matrix. We go back to our home screen, second quit, bring up the RREF once again, hit enter, and you can see we've got all zeros in the bottom row except for that last element. It's non-zero. Really, guys, that's all we need. If we got zeros all the way across, non-zero in that bottom right hand corner, then we know that we have no solution to our system. Alright, so calculator is a great source here. We can use it to check. Please keep in mind, pay attention to directions. If it says reduce the matrix to row echelon form, I'm talking about doing it by hand. And so I've given you some examples here, class discussion examples. Here's one, here's a second, here's a third. I'm going to ask you to work those out with row echelon form, and we'll put those on the board. Or I might provide the answer and we might put some others on the board for practice, but that's what we need to do there. One of the best benefits I feel about doing systems and matrices here is it gives us a chance to do more word problems. Now, I know that you guys may not share that feeling, but I think this is going to be very valuable. They want us to set up the system needed to solve the problem and then use RREF to solve it. Well, I'm gonna change this up here a little bit. Just like I would expect you guys to do, I would expect you to show the work, but let's read this problem and see exactly what we have. Okay, a swimming pool can be filled by 3 pipes A, B, and C. Pipe A alone can fill the pool in 8 hours. So the rate of pipe A is 1/8 of the pool per hour. Alright, that was not what I wanted to happen there. Alright, rate of pipe A, let's just erase that. Try this again. Rate of the pool, or the rate of pipe A, 1/8 of the pool per hour. Alright. Now, if A and C are used together, the pool can be filled in 6 hours. So let's say the rate of pipe C equals C. Alright, so we've got a time of 6 hours. Now the rate of pipe C plus the rate of A will get the pool done. We'll get it filled. So let's see what this gets us here, guys. This gets me 6c plus 3/4 equals 1. 6c equals 1/4. And so with that in mind, if we divide both sides by 6, 1/6 times 6c equals 1/4 times 1/6, we get c equal 1/24. So c needs 24 hours to fill the pipe alone. C needs 24 hours to fill the pipe alone. Now let's see what else it tells us. It says if B and C are used together, it takes 10 hours. Alright, well, let's let the rate of pipe B equal B. And so in 10 hours, we're going to take the rate of pipe B, we're going to add it to the rate of pipe C, and that'll get the swimming pool full. 10B plus 5/12 equals 1. And so 10B equals 7/12, and we divide both sides by 10. B equals 7/120. So it takes B 120 divided by 7 hours to fill the pipe alone. B needs 120/7 hours to fill the pipe alone. And so we need to know, we've got our rates, okay? The rate of A is 1/8. In an hour, pipe A can fill 1/8 of fill the tank an eighth of the way. In an hour, pipe B can fill it 7/120ths. And in an hour, pipe C can fill it 1/24ths. And so how many hours are we going to need to get it full? Well, we add this up, we get 9/40ths times T equal 1, so 40/9, which is 4, and 4/9 hours to fill the pool working together. All right. So, questions on that one? All right, let's look at our next one here. It says a particle moves along a coordinate line with a constant acceleration a. Then at time t in seconds, its distance s of t in centimeters from the origin is given by s of t equal 1/2 at squared plus v sub naught t plus s sub naught. Alright, and so we've got three equations here. We've got if t is 1/2, then my output is 7, and that gives me this equation, 7 equal 1/2 a times 1/2 squared plus v sub naught times 1/2 plus s sub naught. If time is 1, my output is 11. 1/2 a 1 squared plus v sub naught times 1 plus s sub naught. And then s of 17 equals, t of 3/2 rather. T of 3/2 equals 17. So 17 equals 1/2 a times 3/2 squared plus v sub naught times 3/2 plus s sub naught. Okay, and so what's that give us? Well, 1/8 a plus 1/2 v sub naught plus s sub naught equals 7. 1/2 a plus 1 v sub naught plus s sub naught equal 11. And 1/2, actually 1/2 times 3/2 squared, so 3/8 a plus 3/2 v sub naught plus s sub naught equals 17. And so you can put this into your calculator as we've done on the last few, and we find that a equals 8, v sub naught equals 2, s sub naught equals 5. And so we get the equation s of t equals 1/2 times a, getting ahead of myself here, 1/2 times a t squared plus 2t plus 5, and so we get 4t squared plus 2t plus 5 equals s of t. Okay? And then finally, one last example here. Talking about a bird population. A stable population of 35,000 birds lives on 3 islands. Each year, 10% of the population on Island A migrates to Island B. 20% of the population on B migrates to Island C. And 5% of the population on Island C migrates to Island A. Find the number of birds on each island if the population count on each island does not vary from year to year. So let's push this problem on down here just a little bit, and I'll write the answer up here again. S of t equals S of t equals 4 t squared plus 2t plus 5. Okay. And now let's work on our last one here. Get this out of the way. And alright, so let's see what we've got here. We are going to let x, y, and z represent the populations on islands A, B, and C respectively. Okay, and so with this in mind, we're going to take the number of birds on X. Now, 10% of those birds fly away to Island B, and 5% of the population on Island C migrates to A. So we get 5% of the birds that are on Z. And that is now the number of birds that are on X, or on island A. So we take the number of birds on island A, we lose 10% of them, we add 5% of the birds from island C, and that gives us the new count on island A. On island B, we start out with Y, we take away 20% of the birds from island B, we add 10% of the birds from island A, and we get the number of birds on island B. Alright, and then finally we take the number of birds on island C, we take away 5% of the birds from island C, and we add 20% of the birds from island B, and that gives me the number of birds on island C. So my system of equations here, we've got negative 0.1x plus 0.05z. This equals 0. We've got 0.1x minus 0.2y, and this equals 0. And we've got 0.2y minus 0.05z, and this equals 0 as well. So what we have here, we have 10,000 birds. When we work this out, we get a solution of 10,000, 5,000, 20,000. So what this tells me is island A has 10,000 birds, B has 5,000, and C has 20,000. Okay, so a lot to do here, kind of time consuming. That's okay, we can do it. Again, plug this matrix into your calculator, and there may be a couple of these on the test where I ask you to set it up and then use the calculator to solve it. No discussion problems here for these word problems, but definitely some for homework. So set up the systems and then use RREF to solve it. If you have questions, bring them to class. We'll be happy to answer them.